everybody. I think we are slowly getting back to attend in-person seminars, which is a good thing. So thank you, all of you, for coming. It's a pleasure for me to introduce today's speaker. It's Professor Pawel Hawrylak. Pawel Hawrylak is a very well-known scientist, actually, who has been leading the field of nanophotonics, particularly, and especially with semiconductors, structures, nanostructures, wells and quantum dots, and all kind of dynamical studies on this kind of semiconductor nanoscale structures. He is at the University of Ottawa in Canada. He has been there since 8 years ago, but before he spent in Canada almost his entire senior career in the NRC, in the National Research Council of Canada as well. So he has been for more than 20 years in Canada. And before that, he had been developing a postdoc in the 80s, late 80s, in Brown University. And previously to that, he got his PhD in Kentucky University, working on graphene. And we are very happy to have you here and listen to what you have to tell us. Thank you.
Thank you. Thank you very much. Thank you, Javier, for the opportunity to be here. Every day I walk by La Concha to get here, so it's fantastic. I will tell you a little bit of what we are doing in Ottawa, and let me start by maybe how about this? No, how about this? No, I will try the other one. Everything worked before. No,
but you check early, right?
Yes.
Maybe they changed something.
I don't know. Try it.
Let's try now.
Yes. So I walk every day by La Concha, and I enjoy very much the view. If you come and visit us in Ottawa, this is a view of Ottawa Congress Center, Rideau Canal, Canadian Parliament, and the Chateau Laurier, one of the Canadian Pacific hotels. So come and visit us. All right, let's start with why we are doing what we are doing. That is, what are our challenges? So first is our challenge is that we have too many electronic configurations. Yes? It's condensed matter theorist. So imagine the quantum solid. For any theorist, an atom is a box and an electron is a one. So we all know that. If I put 5 of those electrons into 12 solid with 12 atoms, I get about 800 configurations. So that's the size of my Hilbert space. If I increase this size just a little bit, to 240 atoms and 100 electrons, we get about 10 to 70 configurations. And I don't know how you can reach this conclusion, but some people say it's about the number of atoms on Earth. Yes, so clearly difficult challenge. So it is a great challenge, but it's also a great opportunity, because with very few beats, we obtain a lot of resources, and that's why we have IBM Blue and Cube Blue and Xanadu and D-Wave and so on. So there is this huge Hilbert space of a material, and it is in fact possible to tame it a little bit. That is, if entanglement entropy law is satisfied, then the relevant part of the Hilbert space is actually quite small. Yeah? It's actually quite small, so we can have hope that we will actually understand the material. Other challenges: energy efficient electronics and photonics. Yes, this is a critical challenge. Power dissipation. Power dissipation is a critical challenge in electronics that is working today. And if you ask yourself, what is energy required for a 10-minute Google search, it's about as much as boiling a cup of water. Okay? So that's why we are putting all these all these servers next to power plants, right? Because you need to cool them. Where is this coming from? Because current semiconductor technology involves many different materials. So in very crude terms, silicon is for electronics, compound semiconductors, indium and phosphine based, yes. So indium based for optoelectronics, ferromagnets for memory. So all of this, lots of connections, lots of ohmic losses, lots of heating. Yes, if you can boil an egg with your laptop sometimes if it's not cooling properly. So we are thinking in terms of materials, and if you think about a sustainable electronics and photonics, then we have to look at the abundance of the elements in the upper continental crust, because this is where we are getting our materials. Yeah? And if you look at silicon, there is lots of it. Yes, if you look at carbon, there is lots of it. But optoelectronics is based on indium, yes, and this is a rare element. So we need to find some alternatives. Yes? We need to find some alternatives. So, current semiconductor technology, many different materials. It is not sustainable. It is energy inefficient, and it is not powerful enough to answer a lot of problems we would like to find answer to. So, challenges, but now dreams. And who better than Richard Feynman? So, Feynman had actually two dreams. And the first one is we are on the way to realize simulating quantum world on a quantum computer. Yeah? We are heading there. But he had a second dream. I never knew it until I started looking at it. He had a second dream. His dream was to build autonomous nanomachines able to explore the living cell. Okay, to go down to the living cell and explore, repair, and so on. So you need a lot of things to put together to build such a machine, and several people are actually working in this direction. Right, so we are thinking about these challenges and dreams, and we try to address them by designing materials at the nanoscale. What does it mean? Well, we are working on various projects, and one is building quantum circuits based on electron spin. So we take a 2D electron gas, we put gates on top, and then we put localized electrons and control their interaction, build a quantum circuit based on electrons. Connecting spin with photons, source of entangled photon pairs and spin-photon interface, that's an indium phosphide nanowire. This is a quantum dot. Just a regular self-assembled self-assembled quantum dots. They host excitonic artificial atoms and are used for quantum dot lasers. So this is a cross-section of such a quantum dot taken at NRC many years ago. And you can now buy quantum dot lasers. Yes, they have improved temperature dependence, power dependence, and so on. Nuclear spintronics. So almost all atoms have nuclear spin. Yes, and we know nothing about it because it's so isolated from the rest of the world that we don't care. But in reality, it's there. And if we learn how to tap to this nuclear spin, then we have another important quantum resource. So we are working with Hirayama-san at the Tohoku University, trying to understand how to manipulate individual spins with electron spins. Topological insulators, of course, it's not that long ago that we discovered that something was missing in our description of materials, and that was topology. And so we are working on quantum dots in topological insulators, which have very robust edge states and can be used for various sensors, for example. everything that I described here requires molecular beam epitaxy or MOCVD or chemical beam epitaxy, expensive tools that are needed to produce these structures. But of course, there is a lot of interest in printable electronics, and for that, we need different growth techniques, and we generate different structures. So, for example, nanocrystals for photovoltaics and lighting. We work on graphene quantum dots, so nanostructures, how to engineer properties of graphene using shape, size, engineering. And 2D semiconductors, true 2D semiconductors with atomic thickness, mainly decalcogenides, metal decalcogenides. So clearly I cannot cover all of this. I selected a couple of examples, and I have my alarm clock set. Javier told me 45 minutes, no more. So it will ring, and that's it. All right. So what do? We work on quantum dots. These involve millions of atoms, so nanostructures. They involve millions of atoms. So electronic properties cannot be calculated using ab initio methods. So we have to come up with some other alternative tools. Moreover, there are emergent quantum phenomena, properties of material which cannot be inferred from properties of its constituents, yes, various fractionalizations and artificial gauges that appear, and all sorts of exciting stuff. What we do? Well, we do computational design of these materials, working a lot with our experimental colleagues. We use DFT, we use our own code, QNANO, I will describe briefly. We have some other, and of course, the concept of quasi-particles, which makes everything much simpler. Right, so this is our QNANO code. So we start with nanostructure, be it a piece of graphene or an indium arsenide quantum dot or a nanocrystal. Yes? So we define the atomic positions of all constituents, somewhere around 1 billion of atoms. Yes, it's still not very big. 10 to 9 is 10 to 3 times 10 to 3 times 10 to 3. So while we like to think that 10 to 9 is big, in reality, it's still a small structure. And then we do atomistic strain calculations, and then a lot of input goes into defining an electronic Hamiltonian. So from ab initio calculations, and we go from the atomistic tight binding to what we would like to have, effective mass, which is the simplest. Yeah? So we want to go from atomistic at the atom level understanding properties to something manageable, like an effective mass, where we can understand and predict what will happen. And then when we have our electronic Hamiltonian, where we can handle this for about a million atoms of that order. And then, of course, the hardest part is to calculate quasi-particles and response functions. So we use configuration interaction and then physical properties. So multi-exciton generation for solar cells or high excitation optics. That's what we mostly do, because that's what our experimental colleagues do all the time. High bias transport and so on. Okay, so this is our workhorse. And now let me explain some of the projects that we have been working on. And let me start with nanocrystals. So nanocrystals, of course, very important for printed electronics and for lighting. You know, Ted Sargent likes to talk about painting walls and roofs and generating photovoltaics and sustainable economy and what have you. So the problem there is that the challenge was that nobody was able to realize population inversion, and it turns out that the reason was the band degeneracy and Auger processes. So let me describe how we went about using our QNANO, how we went about solving this challenge or addressing this challenge. So if you take a cadmium selenide nanocrystal for different diameters, you will find that the top of the valence band, so I am showing energy levels, 1 electron energy levels, and it turns out that the top of the valence band is not just one level that you like to think, 1s level or a whole. No, it is a band of states. It is a band of states. And okay, so, or shell of states at the top of the valence band. Okay, and if you now look at the population of this shell, so electrons and holes in this shell, then you will find that the chemical potential Fermi level of electrons is tied to this 1s level in the conduction band, but it is pulled into the band gap for the band of states for a given temperature. And what you need is, for gain, you need that this difference be bigger than the gap. Okay. So how do we go about making this happen? So then one more time, this is our situation, and it is not changing if we have biaxial strain. Anyway, we strain it uniform. But if we strain it, pull it in one direction, then we split this degenerate shell into well-defined levels, and this brings the Fermi level into in the valence band into this level, and so there is a hope to achieve gain. Yes, so strain engineering, removal of degeneracy, demonstration of gain, and this is achieved through facet-selective epitaxy, driven by my colleague, slightly younger, Alex Bosch. So this is a picture of these nanocrystals after facet-selective epitaxy, and there is also not only they are. So you see some facets are enhanced versus others. And in addition, there is a chemistry going on with this different molecules passivating the structure, and you go from quantum efficiency of 25% to 90%. So this is how it looks like, this facet selective epitaxy. And now we look at the hydrostatically strained, so in all directions equally, and you see a broad emission spectrum, and then when we biaxially strain, you see splitting of these levels and narrowing of the emission spectrum, because now we just have a single level recombined. And if you pump the structure, you see nice lasing. So using some understanding at an atomistic level of these nanocrystals, we were able to overcome this limitation and demonstrate lasing of these nanocrystals. Carbononics. So this could be in the challenge section, but semiconductor-based optoelectronics involves molecular beam epitaxy of materials and designing optical band gap while matching lattice. So this is a figure that is very familiar to all people in semiconductors. These are different semiconductors, their band gap and the lattice constant. So for example, if you look at gallium arsenide and aluminum arsenide, or any combination of, yes, if you have a mixture of gallium aluminum arsenide, there is basically the same lattice constant, and you can tune the gap. So this is why these materials are essential in discovering various new phases of matter. So quantum Hall effect, fractional quantum Hall effect, or quantum cascade lasers, and so on. They are all based on these combination of materials, and now you see why, because the lattice is almost the same. So you can change concentration of aluminum, but you don't generate any dislocations and defects. Yeah? On the other hand, if you look at in the gap in the range of 1.3 to 1.5 micron, yes, which is your minima transmission for silicon fiber, this is the telecom windows, then you see you have to go to indium phosphide, indium arsenide system. Yes? So that's why all amplifiers, all devices working with optical fiber, all based on indium phosphide. So it is a critical material. But the important part is that we are limited. We are limited in designing our materials by how well the lattices match. Yes? And there is a limited amount of band gaps that are available in nature. So if we could bypass this limitation, yes, if we could bypass this limitation. So what we will discuss is we will discuss now designing optical band gap, but with graphene quantum dots, potentially from UV to terahertz in just one material system. Okay, one material system. So what we are doing is we are taking a piece of graphene and cutting it. Taking graphene and cutting a piece out of it. Yes? So this is, imagine, this is the piece of graphene. Yes, we have PZ electrons running from one carbon atom to another. So tight binding Hamiltonian works very well. We calculate the energy levels of this electron, PZ electron, on this piece of graphene. Surely there is some discrete spectrum. Yes, there is a Fermi level at 0 here and a band gap. Yes, and a band gap. Meaning we calculate then the dipole moment and calculate the absorption of a photon. So when photon comes in, it kicks an electron across this band gap. Right. So graphene quantum dot absorbs, emits light, and of course only photons with energy larger than the band gap are absorbed. So now we take different sizes and we plot this band gap as a function of the number of atoms, which is related to the size, of course. Yeah? And if we look at the highest energies, we cover the ultraviolet, and then we go down to the terahertz. So just changing the size of this graphene quantum dot allows us to cover a very broad photon energy range. Yes? So perhaps this could be very useful for photovoltaics. Also, if I look and compare now these possible band gaps, continuously tuned, almost continuously tuned band gaps, and compare them with silicon, we are somewhere here, indium arsenide, indium phosphide, we are somewhere here, lead selenide, so for infrared detection, nanocrystals, somewhere here, and then terahertz quantum cascade lasers, somewhere here. We can do it in principle by just cutting graphene with different sizes. Of course, there is a little more to it. So could we perhaps replace all known optoelectronic materials with just graphene? I don't know, but it's worthwhile exploring. Now, this dependence of the band gap on number of atoms, yes, can be understood in terms of confined Dirac fermions. So I have Dirac fermions, my Dirac fermion cone, yes, and size imposes some lowest possible allowed wave vector, K star, and 2 times K star is the band gap, and this is proportional to 1 over R, the radius of my quantum dot, and that dependence on number of atoms is exactly that. So in a sense, when we look at this band gap, we are confining Dirac fermions to a different size quantum dot. There is a little bit interesting behavior at small quantum dots where the the benzene character of our building block starts playing a role, and there are different edges that affect the properties. It's quite interesting, but I will not bore you with that. Okay, so the basic idea is that we change the size of our graphene quantum dots, and this involves different wavelength of light coming out or being absorbed. Okay, so now this was all very simple. Of course, there is a lot of calculations that go before we make such statements. Let's talk about these. Take these graphene quantum dots and start asking a question of how their properties change as a function of shape. As a function of shape. So what we will describe is how one can build a synthetic quantum Hall system. A synthetic quantum Hall system. Why want to build a synthetic quantum Hall system? Well, you take a gallium arsenide, gallium aluminum arsenide quantum well, you apply a strong perpendicular magnetic field, and you convert the continuous electron spectrum into a set of Landau levels. And if you put electrons into a lowest Landau level, the properties of this electronic system depend on the feeling of this Landau level. We have fractional quantum Hall effect, which is just a manifestation of very, very strong correlations in such a degenerate shell. So we can convert our system into a strongly correlated system if we are able to build this synthetic quantum Hall system in graphene. So this is what we do. We take just a reminder. If I have my circular like graphene quantum dot and I calculate the energy spectrum, I have dense spectrum of discrete levels up to the Fermi level. So this is a field valence band or a place for holes. And then I have a conduction band, empty conduction band, a place for electrons. If, however, I deform this structure to a triangle, we find that this continuous spectrum across the Fermi level collapses to a degenerate shell. And this degenerate shell, its degeneracy depends on the size of the quantum dot. So it can be engineered by changing the size of this quantum dot, the number of states or the number of states in my quantum Hall level changes. That this implies that it's a flat band. There are electrons there, one per state. So it implies flat band magnetism. Yes? At a fractional feeling, it implies strong electron-electron correlations, maybe something like fractional quantum Hall effect, but at zero magnetic field. So we are engineering a strongly correlated system at zero magnetic field.
Can I ask you something?
Yes.
So the question mark in the previous slide has been answered, or is just something that you're investigating?
I will show you the answer.
Okay, because my question is that while somehow I understand that you get something flat and the correlation are becoming important, with all the magnetic field, you are not achieving a fractional number. So how can you then compare this to the fractional quantum Hall effect where the Chern number plays an important role?
What is important here is the dependence of the appearance of gaps and compressible and incompressible states as a function of filling factor. So that's what we will see in a moment. Okay, so that's for me a fractional quantum Hall effect. A fractional quantum Hall effect is where, as a function of filling factor, there appears gaps in a spectrum where there are no gaps, no incompressibility at the different filling factors. So let's try to illustrate this. There are different points of view. So now let's try to understand what happens by looking at an energy gap of n added electrons in a degenerate shell. So I have the degenerate shell, I bring in a gate, I take the electrons out, and now I am putting electrons in one by one. Okay? This is what we do also in the fractional quantum Hall effect. Okay? Fix the magnetic field, and with a gate, load the system with electrons. So I will look at the gap, energy gap, okay? And this gap is zero in the absence of interactions because I am adding an electron with energy E0. I am adding a second electron with the same energy E0. So the difference in energies is zero because I am adding electron with the same energy. Yes? So the gap is zero, okay? And now I am turning on interaction. And this gap now oscillates, varies with the filling of this shell. At half filling, the gap is largest, and also the magnetic moment is largest. So you engineer both gaps and spin, total spin of the system. Okay? All right. Okay, so we can engineer properties of material. By that I mean the gap, the spin, by changing the filling of this degenerate shell. Now, this is related to the magnetic moment I mentioned. Yes, is related to the Leib's theorem describing ground state spin of a bipartite Hubbard model, and this on a bipartite. So even though a graphene is all composed of carbon atoms, we can paint some of them with red and some of them with blue. Yeah? These are two triangular lattices that form the hexagonal lattice, and if we paint them, they are the same, but we will now paint them. Then we can count red and blue, and if the difference between red and blue is finite, we expect to see a total spin. So at least the spin is known. The single particle spectrum of the shell has been derived, so we know what it is, and the rest is exact diagonalization. So we can engineer spin, magnetic properties through sublattice engineering, and this means that we can integrate electronics, photonics, and spintronics in a single material, these graphene quantum dots. Yes? And because we can do this at nanoscale, we potentially, with this approach, we could realize Feynman dream of nanomachines, because you can take a piece of graphene and make it a light emitting diode. You can take a piece of graphene and engineer it to have a magnetic moment, and either one of them acts as a conductor if we attach leads to it. So we could engineer atomically thin structures, also laterally very small. Okay, and also here there is work in trying to make these structures, so triangulines or non-Kekule molecules and so on. This work is moving forward. So this is a picture from Jiang Lu from Singapore, but there is a lot of at EMPA and also here. Very nice work. All right. Macroscopic quantum states in semiconductors. So come to think of that, what will happen to about $300 billion semiconductor industry if quantum computer is based on aluminum or niobium? Why are we making superconducting quantum computers right now? Because we take advantage of the fact that superconductivity is a macroscopic quantum phenomenon. So how can we build structures or design a qubit based on macroscopic quantum state? Macroscopic quantum state in a semiconductor device. All right, let's see how this goes. So what we will do is we will go through a design of a synthetic spin-1 chain. Now, synthetic spin-1 chain is a paradigm for topological quantum matter. So irrespective of the qubit, it's an interesting problem to look at. And we will do this, we will show that this is a macroscopic quantum state, this synthetic spin-1 chain in a semiconductor device. We will also use the Haldane quasi-particles to construct the qubit. So this is the basis of technology from Dan Dalaku and Philip Poole, my colleagues at NRC. So you start with indium phosphide substrate. You, in a specific location, put a gold nanoparticle in this opening, and then you deposit indium phosphide. You start depositing indium arsenide, and you create a quantum dot in an indium phosphide nanowire. The nice thing is you can clad it, and then you have this quantum dot coupled to a photonic cavity that can be directly coupled to an optical fiber. Yes, it's all indium phosphide. Remember, to couple to the telecom network, we need to work with indium phosphide. This is an ability. This just demonstrates an ability to create an array of quantum dots. Here, each quantum dot is different, so that they have a distinct optical signature. All right, so we have a quantum dot. This quantum dot, we can generate an array of these quantum dots. And the nice thing about these materials is that we know the position, we know the shape, we know the diameter, we know the height, and we know the average arsenic concentration. So the arsenic replaces phosphine, but we don't know the arsenic versus phosphine profile. And also the problem is that the Wurtzite lattice structure plus the size of our quantum dot. But this is a nanostructure about which we know a lot. Okay? Not everything, but a lot. So we have a single particle Hamiltonian. It's a tight binding Hamiltonian fitted to the ab initio results. And then we have the multi-electron hole interaction Hamiltonian. And all of this is handled in our QNANO code. So the properties of these materials are such that we have a relatively small arsenic concentration. So here you see arsenic atoms from the top. The wire is hexagonal cross section, and this is from a side. So you see this is far from perfect. This is far from perfect, and each dot has a slightly different place for the arsenic atoms versus phosphine atoms. So despite this disorder, the shell structure in conduction band appears. So you have an S-like, you have doubly degenerate P-like, almost degenerate D shell, and so on. Yes? So, and this is, you do this for hundreds of those dots with random distribution, and they all have this shell structure. So we put 4 electrons into this quantum dot, and 2 of them fill the S shell, and then 2 of them occupy the P shell. P shell is degenerate, So the exchange interaction aligns the spin of electrons on a p-shell, and therefore each quantum dot with 4 electrons has a ground state with spin 1. So even though we start with 4 spin 1/2 electrons, in the end we get spin 1, and we know this for a very long time. Now we bring together 2 of those dots, and this is a picture of this p-shell of a double dot. So we see, okay, there are these 2 p-like states, and they are in one layer, in the second layer. This is side view. And now we put 8 electrons into these 2 dots. So 4 into one, 4 into the second one. We compute, there is a Hilbert space, is, I don't know, 100 million by 100 million, something like that. We compute the ground state, and we see the ground state is a singlet. The excited state is a triplet, and the next excited shell is a quintuplet. So singlet, triplet, quintuplet, and we can think of this as effectively 2 electrons on a p-shell in one dot interacting with 2 electrons on a p-shell on the second dot, and effectively this is a Hamiltonian of 2 spin 1s. 2 spin 1s. The Hamiltonian of 2 spin 1s, Heisenberg Hamiltonian of 2 spin 1s, gives exactly this spectrum. And from this microscopic calculation, we obtain the coupling constant J. So now we have a single spin 1. We now show that the 2 spin 1s interact through the Heisenberg Hamiltonian. We are on the way to study this spin 1 chain. So now we just studied the spin 1 chain, and what do we see? As a function of number of these quantum dots of spin 1s, we have an oscillation of between singlet and triplet, which goes down to 0. And so ground state is in a thermodynamic limit 4-fold degenerate, and separated from these hundreds of millions of states by what is known as a Haldane gap, a gap from ground state to the quintuplet. This gap is about 0.4 of this exchange coupling which we computed. Yes, so we have triplets, singlets, and 4-fold degenerate ground state, so you can do something with it. Yes? How do we understand this 4-fold degenerate ground state? We look at the expectation value of spin. Okay, so this is an expectation of value of spin in a ground state. That's a function of site. And now if we look at the edge, we see that the spin at the edge is half. We started with spin 1s, but a collective state of this very large quantum system is such that at the edge there is a spin 1/2, quasi-particle with spin 1/2. These quasi-particles, there's another one spin 1/2 here, 2 spins 1/2. 2 effective spins 1/2 is 4 states if we combine them, yes, and that exactly reproduces the degeneracy of this quantum system. And now, so we have these fractional spin quasi-particles, and we can forget about everything else and just focus on these Haldane quasi-particles at the edges, and they know about each other. This is a quantum system that extends over macroscopic distance. So I have a 1 meter long wire, and this one here, Haldane quasi-particle, knows about this Haldane quasi-particle. Yes, right. This is almost over. Yes, so I have these fractional spin quasi-particles, and you can create a quantum level 0 and quantum level 1 with these 2 spin quasi-particles. So this is a so-called singlet, triplet, qubit, but now made of topologically protected Haldane quasi-particles. Okay, how do I get to the end? We can do TIGH chain, various other things. I will just go quickly through this.
You can have 5 more minutes, Pawel, to relax.
5 more minutes.
I'm all 10.
You are giving me more time
I think so.
on behalf of the audience. Open the door. Let's see how many will run away. Okay. All right. I know you have to blame Javier. I will go very quickly. So this was a singlet triplet qubit. There is another path to a perhaps more efficient spin qubits, and that's these are okay. I need to go here. So we were working with these quantum circuits in gallium arsenide for a very long time. They were developed in Ottawa at the NRC. Now what we are doing is we are putting these gates on top of 2D semiconductors. So now there is a spin valley qubit that will be localized in the single atomic thickness layer, and so its interaction hyperfine coupling will be strongly reduced, and all the energetics will be strongly increased. Energy level, spacing, stability, and so on. It's not so easy to make it. We are working on it 3 years already. So our friend Klaus Enslin has made very nice progress. Philip Kim also making these structures. There are others, and our first results are here. So how do we compute? Well, how do we simulate these spin valley qubits? This is our QNANO computational box. So we create a box with for example, tungsten in selenium dimers, and then we apply periodic boundary conditions. This selects the wave vectors and generates band states for each of the wave vector. So these are the states. Remember, the conduction band in these materials is complex. For each K point, there are 3 Q points that surround. So it's a little bit like a quark physics, but it's a complicated band structure, and we are then putting on top of this band structure a top gate, and this is a top gate. We expand quantum dot wave function in these band states here on the conduction band, and calculate quantum dot energy levels by solving this integral equation. And here the potential confining electrons contains topology of the wave function through a band contribution. So these are the spectra. They are characterized by the following properties. There are 2 valleys, 2 non-equivalent valleys. Then there is a spin orbit splitting. So the spin up and spin down states are split. Then there is a topological splitting of states which have different angular momenta. So turning to the right or turning to the left, they effectively sense the magnetic moment, topological magnetic moment. Then there are these Q valleys per each K valley that generate another set of states. And then the question is, how will electrons fill these electronic shells? Well, we do this by studying this interacting Hamiltonian. The Coulomb interaction is either directly screen Coulomb or Keldysh screen interaction. The kinetic energy is proportional to omega, the level spacing, while the Coulomb energy is proportional to square root of omega. So by changing the level spacing, we can change the role of the role of Coulomb energy versus single particle energy. So omega controls ratio of T over D. We build configurations, we diagonalize our Hamiltonian and calculate ground and excited states. And now we can answer the question of how electrons fill electronic shells. So at large omega, They just feel it normally, so minimize the kinetic energy. When Coulomb interactions start to play a more significant role, we find a intervalley antiferromagnetic phase. So you have a spin polarized state in one valley and oppositely spin polarized state in the non-equivalent valley. And then at very strong interactions, we find valley spin and valley polarized broken symmetry states. And that is something that we think we have seen before in magnetoluminescent experiments on tungsten disulfide, where I think the valley polarized state of two-dimensional electron gas was seen. So to come to an end, we are trying to design materials and devices at the nanoscale, and I talked about nanocrystals. I talked about carbononics and maybe a path toward fulfilling Feynman's dream of nanomachines. I talked about how you could make a macroscopic quantum state in semiconductors using Haldane and Majorana quasiparticles. And then I talked about 2D materials and controlled electronic systems in 2D materials with spontaneously broken symmetry states. And let me finish by thanking you and all my colleagues who contributed to this work. Thanking you for your attention. Thank you.
Very much. I think it was very interesting, very clear. I appreciate it. Time for questions. Audience. Roberto.
Very nice talk. I really enjoyed the talk. However, I have a question here. You're showing us huge, massive systems that are strongly correlated. I wonder, how do you account for the electron correlation? How do you include that in your calculation?
We do configuration interaction.
With that huge system?
With which huge system?
For instance, the graphene nanofragment.
Yes, the shell is the number of states in the degenerate shell. So there is a whole process, but boils down to the number of states on a degenerate shell. The one that we studied is of the order of 7 to 10. Yes, so you have a degenerate shell with about 10 states. That's something that we have been doing on a Haldane sphere, for example, for a very long time.
Okay.
So configuration interaction on a limited Hilbert space, limited to the degenerates.
Okay. I see. Thank you.
Not all the electrons.
No,
that we can't.
Any other questions?
Not, I would like to ask.
Yes, please.
Have you tried, talking about the graphene nanofragments, have you tried to dot the system with boron or nitrogen atoms?
We have not done this. No, we studied as a function of size, but not doping. Yes. I understand it leads to interesting phenomena.
More questions? I have one myself, maybe more, not philosophical, but practical, about the use of all these solid state quantum dot systems for quantum, for generation and manipulation of qubits and so on, right? That you have probably gotten several times as a community, right? We have several efforts. You mentioned superconductors as macroscopic states, which become easy. There are other candidates to deal with qubits and ions and so on. So how do you see the evolution of your field, quantum dots and qubits in solid state systems like this, which obviously have their advantages, but also their disadvantages with inhomogeneity and losses, and what is your vision, your honest vision, of course, all this cannot be on the way, but about the evolution of this manipulation of spins and states in quantum technologies. Is this a real candidate for future or not compared
so in terms of building a quantum computer with with spins. Of course, we know we have been doing this in gallium arsenide. There is nuclear spin, so it's very difficult to increase the coherence time. On the other hand, you in these 2D materials, hopefully the hyperfine coupling will be reduced to zero, and then we still need to understand the role of Valley, but there is a potential of making useful devices with spin in these 2D materials. For photon entangled photon pair, for example, generation and single photon sources, there is a lot of interest. So temperature, yes, there's temperature, and there is coupling to a silicon fiber. So you can do free space and perfect, but all our infrastructure is on based on silicon fiber. And so it has to be indium phosphide based materials. All telecommunication is based on indium phosphide. So if you want to make a useful source of coherent entangled photons, it needs to go into a fiber. So
you are constrained.
So that's a constraint, yes. So you know you see beautiful work being done, but it just goes on a shelf. Yes? But if you want to make something practical, it has to go into a fiber.
Okay. Thank you. Any other questions? Yes, please go ahead.
Maybe a naive question about graphene quantum dot. Not the one you were talking about, but let's imagine that you make graphene quantum dot with electrostatic confinement. So there is a barrier, but it's still graphene in the barrier. In the beginning of the graphene era, there was a lot of discussion of Klein paradox, which means that if you have a Dirac electron, then it would not be reflected by a barrier. And then apparently you cannot confine an electron in such a quantum dot made of graphene, unlike in a conventional semiconductor. Could you comment on this?
Yes, yes. So I didn't show any gated single graphene layer, but bilayer graphene is a perfect medium for building spin valley qubits. So we also have Klaus Enslin and group and Christoph Stampfer, they are building beautiful bilayer graphene quantum dots. Because you open the gap with electric field, you open the gap, and then it's just like gallium arsenide.
But does the Klein paradox really exist? Can you confine electrons in a single layer graphene with Dirac spectrum by making?
My understanding is not.
Was it demonstrated, the impossibility of that?
It's difficult to demonstrate an impossibility of something. Somebody else who is smarter than you can come up with an answer. So it's impossible to. I think everybody accepted that this will not happen. So I was only showing finite structures where confinement is obvious. But
okay,
my feeling is that you cannot, due to Klein tunneling, use single layer. So that's why everybody is using bilayer, and they are very successful. We have not been successful yet, but Klaus is doing fantastic work.
Very good. So I think if there are no more questions, I checked there are no more questions in the chat neither. So then I think we just thank you again, and thank you very much.
Thank you very much.
Me dijo que te la pasaba aquí, no sé si quieres que vaya de nuevo.
¿Tienes
por
cosas
ella.
ahí que...?
Él para la reunión de mañana.
Pues pregúntale a...
Es que estaba en reunión.
Vale, pregúntale a ver si
It's not responding to my fingers.